Today we're going to be exploring two sample t-intervals for the difference in two means. This is section 10.2 of your textbook and in our unit 7, day 2. First, let's look at our check your understanding from last class. Biologists studying the healing of skin wounds measured the rate at which new cells closed a cut made in the skin of an anesthetized newt. I don't know how to say that word. Anesthetized. Here are data from a random sample of 18 newts measured in micrometers or micrometers, millionths of a meter per hour. Bunch of numbers here. Says calculate and interpret a 95% confidence interval for the mean healing rate of the mean for the population mean. So before you do anything, put this data in your calculator. So if you're doing this with me along with the video, pause the video, go into L1 and enter those numbers carefully. Once you have it done, unpause. Now, when you put in those numbers, you're going to go to your stat menu, go to one variable stats, one var stats, and you'll see the 25.666 as your mean. That's your point estimate. And I also want you to go to your stat plot. So second y equals, turn your stat plot on, press zoom 9, just get a look at that graph so you can kind of see if there's any strong skew or outliers. Those are important as you're analyzing data when you're trying to estimate a mean. Make sure you can do both of those and then move on. So as far as writing, we want to make sure we say one sample t-interval for mean. Mean is a true mean healing rate in micrometers per hour in newts. We want to check our conditions. So we got random, 10%, and normal. Random, it was a random sample of 18 newts, 10%. We can assume 18 is less than 10% of all newts. And the approximately normal is what the graph is going to be because we only have 18, so we don't have 30. We don't meet the central limit theorem, and we don't know anything about the population. So it says we get our sketch from the graph. We see there's no strong skew or outliers, and if that's the case, sketch it out. Doesn't have to be labeled. You sketch it out. You say no strong skew or outliers, approximately normal, and you can move on. As far as your calculator goes, go to one stat tests. Go down to t-interval. I believe that's option 8. Stat test 8. And you just get that in there. You report your t-interval. Your interval is going to be 21.527, 29.826. Your mean is your point estimate, 25.667. Degree of freedom is always one less than the sample size, so it's 17. And your t-star, you can get from inverse t. Remember, you can go there and go to second vars 4. And I just do 1 plus 0.95. I average out with 1, so 1 plus 0.95 divided by 2. And your degree of freedom will be 17, since it's 18 newts. Then you can click paste, and you can see about 2.11. So that's all you really need. You get your interval, you report your mean, your degree of freedom, your t-star, and then you summarize. Let me say we're 95% confident the interval from 21.527 micrometers per hour and 29.806 micrometers per hour captures the true mean healing rate of newts. So that is the process for estimating a population mean for one sample. Now we're going to do two samples. So we're trying to find the difference. So let's look at chocolate chip cookies. Let's say you were in class and I gave every one of you a Chips Ahoy cookie and every one of you a Walmart brand Great Value chippers. I think that's what they're called. And we want to see if there's a difference in the number of chocolate chips. So we randomly select a chocolate chip cookie from both. Count the number of cookies, report number of chocolate chips, and report our data to the class. So then, of course, we're not in class. So here's some made up numbers. Suppose we have a class of 28 students. Each student counted the number of chips in a Chips Ahoy and the number of chips in a Walmart brand and reported their findings. So here's what we got. Let's say you counted 22 chips in the Chips Ahoy, 18 in the Walmart chippers, and combined with the class, we have the following data. We have a mean of 21.56 for the Chips Ahoy and 18.22 for the Walmart. And the standard deviation, sample standard deviation, 2.49 for the Chips Ahoy, 4.51 for Walmart, and both sample sizes were 28. We want to calculate that difference. So our point estimate would be 21.56 minus 18.22, which is 3.34. That's a statistic, not a parameter. So remember that we are estimating, so we have to go a little bit above and below to get that margin of error, or to get that interval. So if we repeated this process and we have a sampling distribution, recall that the shape, center, and spread is what we're looking for the shape to be approximately normal. It says the population distributions are approximately normal, so we have that information for us. The center is the population mean subtracted, but we don't have that, so we don't know it. We're trying to estimate it. The spread, remember this formula from our formula sheet is when we do the population standard deviation squared divided by its sample size plus the other population standard deviation squared divided by its sample size, all under the square root. Well, again, we don't have the population standard deviation, but we do have the standard error because we know our sample standard deviations and our sample size. So we can actually calculate this. This is our standard error. And that's on your formula sheet. So we check our conditions. Has the random been met? Yep, it says the samples are random. Do we meet the 10% condition? Sure, 28 is definitely less than 10% of all Chips Ahoy and Walmart chippers. So we write that down. Make sure you check it for both. What about approximately normal? In this case, it says the distributions, the population distributions of the number of chips are approximately normal. So we actually were given that. So that's all we need to say. We just jot that down and we move on. Make sure we check all that for both samples. So we don't just say population distribution. Population distributions is, use those plurals and write them both down so you're getting credit for checking both conditions. Recall our data. I just kind of copied that up here. Now let's construct the interval. There's a lot of steps in this. Of course, this is the 4-step process, right? We want to construct the interval, but remember the formula for a confidence interval is statistic plus or minus a critical value multiplied by the standard of error. Remember that is the margin of error. This, let me annotate on there. This right here, that's your margin of error. So it's your statistic plus or minus your margin of error. So we got to get our critical value. That's going to be a T star. And our standard error is the formula prior to. So, so we do the sample mean subtracted plus or minus T star times the standard error formula. Let's plug in our, before we plug in our numbers, let's get T star first. So remember, you can use table V or inverse T. With table B, make sure you go to the 95% sea level and go to the degree of freedom of 28 minus 1, so it'd be 27. But you can use inverse T in your calculator. Just go to second bars, and then you can do inverse T. Average that 0.95 with 1, and put 27 for your degree of freedom. And you get about 2.0518. So all of that can be plugged in, 3.34 plus or minus 2.0518. Times the square root 2.49 squared over 28 plus 4.51 squared over 28. Take a minute to calculate that and actually see if you can get a lower and upper end of that interval and share that and see what you get. Pause the video if you need a second to put that in your calculator and compute it. So pause it when you're ready. I got 1.34 to 5.34. So when I'm doing that by hand, using the formula, crunching the numbers by hand, I get 1.34 to 5.34. Now there's a little bit more work, doing that by hand. So I suggest using your calculator menu. Go to Stat Tests, go down to 0 to Sample T Interval. See if you can find that in your stat menu. Now we don't have all the raw data, so you're going to scroll over to stats, then you can input these numbers: 21.56 for X1, 2.49 for SX1, 28 for N1, and repeat the numbers for the Walmart chippers: 18.22, 4.51, and 28. Keep your C level at 0.95. We don't do anything with pooled, so keep it at no. Pooled is just assuming you're combining your data. We use that for tests, but not for intervals. So keep it at no. And then go down to calculate. Report your interval. What do you notice? You might notice it's a little bit different. Look at that. The lowest number is 1.375 versus 1.34, so it's a little bit higher on the low end, and the highest number, 5.305, is less than 5.34, so it's narrower. And the reason it's narrower is because of this degree of freedom. The calculator is giving you a degree of freedom of a little over 42.06. That's different than our 27, as we did. Well, calculator uses a different degree of freedom. When they do it in the stat menu, when we do it by hand or using the formula, the degree of freedom is it's the conservative degree of freedom, which means that we are a little bit lower and higher, and that gives us more, I guess, wiggle room to make sure that our mean is in there. But the degree of freedom, the 27, is the smaller of the two samples. So since they were both 28, it didn't matter. But if one of them was like 24, you'd want to use 23 as your degree of freedom. So since the degree of freedom, just by hand was 27, well, that is the smaller of the two samples, but that gives you our interval 1.34 to 5.34. The calculator is giving you a larger degree of freedom. It doesn't use the conservative estimate, and that's okay. But if you plan on using the stat menu to construct your interval, which I still would recommend because it's a lot less work, you don't want to report T-star, because T-star depends on your degree of freedom. And if you're going to, if you're going to calculate your degree of freedom based off of, 20 n minus 1, and you plug that in, you're going to get a different T-star. I'll show you here on the calculator. So let's say we use the calculator's degree of freedom, 42.06. Now, if I did inverse T, and I did my degree of freedom as, was it 27, you can see that T-star was 2.05. But if I did it again, and I did, what was it, 42.06, it gives you a critical value of 2.01799. That's a smaller critical value, so it's gonna narrow your interval. So the calculator does not use the conservative estimate, and like I said, that's okay. You just, if you were to report your degree of freedom from your calculator and the interval associated in your stat menu, then you don't want to say what T-star is based off of inverse T or the table that you did with the conservative degree of freedom. So leave T-star as T-star, basically, is what I'm saying. And it's okay to use the calculator interval. It's more precise, but less conservative. So it'll be more precise. It's still the same confidence level. It's honestly some calculations for that degree of freedom, which I have no idea how it was gotten. So I actually had to look it up, and I'll show you that formula. But again, if you're using the calculator, don't run it by hand and then check in the calculator, because they're going to be different. Okay. If you're using the calculator, do the following. All right, write the formula down. And plug in what we have. We have our difference, our 3.34, your standard errors, your standard deviations, and their sample sizes. Just leave T-star. Leave it as T-star. Write your interval, write your degree of freedom, and you got it. So you can do all that, just leave T-star as T-star. Always write your degree of freedom. If you write your degree of freedom as 27 and you use a different T-star, but you report your calculator interval, you will get docked points on a free response question. All right, so the question is there convincing evidence that there's an average number of chocolate chips in Chips Ahoy and Walmart cookies? Well, using either interval, whether you use the conservative estimate or your stat menus, less conservative, you can see that both intervals are above 0. And so since all plausible values are positive, we do have convincing evidence of a difference in the average number of chocolate chips between the two brands. Remember, if 0 is not in the interval, there is convincing evidence. So what are the important ideas? Well, it's kind of similar as before. We have a parameter, conditions, and formula. The parameter is the true difference in mean based off of whatever context you're talking about. Conditions, always checking for both samples, random, normal, random, 10%, and approximately normal. And the formula, which, this is not on a formula sheet, but the individual components are. So you just have to know the difference of two means, sample means, T-star, standard error formula is on your formula sheet. And you go stat tests 0 for two sample T interval. Just remember, if you're using the stat menu, only report the degree of freedom, leave T-star as T-star. You don't want to get them off. And if you're using the conservative, n-1 of the smaller sample, calculate it using the formula. If you're going to be conservative, you can't use your stat menu to get the interval because it's going to be off. So if you're interested, I had to look this up earlier. That is the formula for the degree of freedom. Don't ask me how it was computed or what person sat down and decided that was what was going to get used. But if you're interested in knowing the history behind that, look that up. I didn't feel like looking that up. Here's your question. Here's your check your understanding. Mr. Wilcox's class performed an experiment to investigate whether drinking a caffeinated beverage would increase pulse rates. 20 students in the class volunteered to take part in the experiment. All of the students measured their initial pulse rates in beats per minute. Then Mr. Wilcox randomly assigned the students into two groups of 10. Each student in the first group drank 12 ounces of cola with caffeine. Each student in the second group drank 12 ounces of caffeine-free cola. All students then measured their pulse rates again. The table displays the change in pulse rates for the students in both groups. So what we have is change in pulse rates based off of drinking caffeine and not drinking caffeine. And you can see the mean changes here are already given. It does not give you the standard deviation. So unfortunately, we do have to go in and calculate those using your stat menu. But you can see these numbers here. And we're trying to see if there is a difference. So construct and interpret a 95% confidence interval for the difference in true or mean change in pulse rate for subjects that like those who drink caffeine versus who drink no caffeine. So before you do any of this, before you do any writing, we are going to enter data into your L1 and L2. So if you have not done so, pause the video and get these numbers typed into your L1 and L2. Once you have those typed in, unpause it and move forward. Do this part first. Once you've read the problem and you see the raw data, go right to the calculator before you do any conditions. Because what you want to do is you want to check that graph. You want to see, is the graph going to support the normal condition? Because if it doesn't, then you can't really do this. You have to kind of, first of all, be there. So let's take a look at first the graph, if I can get that to load here. Sorry about that technical difficulty. So yeah, you want to put these in your stat menu, stat edit, type those in very carefully, make sure there's no typos. Then you want to turn on your y equals, second y equals. Make sure your plot 1 is to the first box plot, and go to second y equals again, and then go down to plot 2, because we have 2 sets of data. So we want to turn that one on, and you also want to hit the box plot here, and make sure that your X list says L2, so you do second 2 for that. Then you can do zoom 9, and you can see both of those graphs. So you can see that the blue graph here, that's going to be the caffeine. The red graph is the no caffeine. And what we're looking for is no strong skew or outliers. I don't see any outliers or any really strong skew. They're fairly symmetric. There's a little bit of skew here, but it's not strong. So those are good sets of data, but that's important because we only have 10 data points for each one. So you have to go by the sample for that approximately normal condition. Let's go back to the So we want to do zoom 9, get a look at the data. We need to know whether the samples have any strong skew or outliers to meet the approximately normal condition. Get that out of the way first. You don't have to write that down yet, but get out of the way first. Then you want to run the interval. You know, you can do, since you have your data in the calculator, you can go to stat tests, which is 0. You can go 0, 2 sample t intervals, 2 samp t int. And since your data is already in L1 and L2, and we want a 95% confidence interval, go down to calculate. And you can just get that, you can jot, you know, maybe on a separate sheet of paper, jot that down, jot your interval, jot your degree of freedom, jot your sample means and standard deviations. You can have all that information and your sample size. That's everything you need right there. So aside from the formula, that's everything you need. So we'll come back to that. Once you have all that in there, now you can start doing your writing. So we have our interval. It's negative 1.3 to about 3.7. Degree of freedom's just a little bit under 18. And remember, our sample size was 10. So if you're doing the conservative degree of freedom, it'd be 9. But this is using that very complicated formula that your calculator will use. It does not use the conservative degree of freedom. That's okay. Here's what you get to write. You do your P, 2 sample T, you write down what you're doing, 2 sample T interval, and I labeled UC minus UN, caffeine, non-caffeine, and I define it as a true difference in mean change in pulse rates for students who drink caffeine versus who do not drink caffeine. Then check the conditions, random, both groups are randomly assigned, 10%, both groups are of 10 are less than 10% of students who drink and do not drink caffeine. Approximately normal, just sketch those. That's where the graphs come in. You already have them in there. So sketch them out. You got them. Write your formula down. Plug in your numbers. Leave T star as T star. Don't have to write that. Then get your interval from the calculator and write your degree of freedom. And then summarize. We are 95% confident the interval from negative 1.3 to 3.7 BPM captures the true difference in mean change in pulse rates for those who do and do not drink caffeine. While this question didn't ask for it, think about what this interval contains. Right, it has 0 in it. So is there convincing evidence there's a difference? According to our data, no. But I'm certainly not a scientist, but I would assume caffeine does have an effect on pulse rates. So maybe the samples are bad. You know, not all intervals are necessarily going to be accurate, but this is from our data what we have. So you have enough information to complete the sapling assignment. Good luck. Ask for questions if you have them, and see you next class.